October 1944, Puget Sound Naval Shipyard, Bremerton, Washington. The acetylene torch cast dancing shadows across the steel plating as Frank Morrison, a 42-year-old welder earning $13 per day, stood back and examined his work with growing frustration. This makes no sense whatsoever. We are building these destroyers with hulls that will not survive what is coming. The Japanese are desperate now, and desperate men do desperate things. He had just witnessed something that made his blood run cold. A confidential Navy briefing delivered to senior welders and supervisors described a new Japanese tactic emerging in the Pacific. Pilots deliberately crashing explosive-laden aircraft into American warships. The briefing officer, a young lieutenant fresh from Pearl Harbor, had shown photographs of damaged vessels. The images were horrifying. Massive holes torn in ship hulls, fires raging through compartments, sailors burned beyond recognition. The officer's voice remained clinical and detached as he explained the threat assessment. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Intelligence suggests this tactic will increase in frequency and intensity as American forces approach the Japanese home islands. Current destroyer hull construction provides inadequate protection against high-velocity impact, followed by explosive detonation. Ships are surviving the initial collision, but succumbing to secondary explosions and uncontrolled flooding. The Navy is evaluating design modifications, but implementation will take months, possibly years. Morrison had built enough ships to understand what those words meant. The Navy knew the current designs were inadequate but lacked a solution. More importantly, they lacked the time to develop and test new approaches through normal engineering channels. Ships were needed now, not after months of design reviews and prototype testing. Walking back to his workstation through the vast construction bay, Morrison could not stop thinking about the problem. The current destroyer hull design was fundamentally sound for conventional warfare. Single-layer steel plating, properly welded and braced, could withstand gunfire, shell fragments, and even torpedo near misses if the damage control teams responded quickly. But a kamikaze attack is different. The impact velocity alone would punch through single-layer plating like paper. Then came the real killer, the explosion. Japanese aircraft carried hundreds of gallons of aviation fuel, plus whatever additional explosives the pilot could load. That combination, detonating inside the hull after penetration, created devastating results. The explosion expanded in all directions, but the path of least resistance was inward, deeper into the ship. Blast forces ripped through bulkheads, ignited fuel and ammunition, and created pressure waves that could crack a ship's keel. Morrison had seen the aftermath of such damage when the destroyer USS Hugh W. Hadley limped into Puget Sound for repairs in August 1944. The ship had survived a kamikaze strike off Saipan, but barely. The impact had torn a hole 15 feet wide in the port side. The subsequent explosion had gutted 3 compartments and killed 28 sailors. The ship survived only because the kamikaze had struck near the stern, away from critical engineering spaces. Had the impact been amidships, near the boilers and magazines, the Hadley would have joined the dozens of other ships resting on the Pacific floor. That evening, Morrison sat in his small rented room in Bremerton, sketching hull designs in a worn notebook. His wife, Margaret, had died 2 years earlier from pneumonia. His son, Daniel, was serving somewhere in the European theater. He could not say where due to censorship. Morrison lived alone, worked 12-hour shifts, 6 days a week, and spent his evenings thinking about problems that kept other men awake at night. The solution came to him around midnight, so obvious he wondered why Navy engineers had not thought of it already. The answer was not stronger steel or thicker plating. The answer was layers and spacing. Think of it like armor on a medieval knight, Morrison muttered to himself as he sketched rapidly. One thick plate of armor is strong, but a sword can pierce it with enough force. But multiple layers of armor are separated by padding that distributes the impact force. The sword penetrates the first layer, but loses energy. The padding absorbs shock. The second layer catches what remains. The same principle could work for ship hulls, but with a critical modification. Instead of padding between the layers, use empty space. When a kamikaze penetrates the outer hull, the explosion expands into that empty space. Most of the blast energy dissipates in the gap, instead of propagating deeper into the ship. The second hull layer, positioned 6 to 8 feet inboard from the outer hull, catches the weakened blast. A third layer, another 6 feet inboard, provides final protection for critical spaces. Morrison spent the next 3 days refining his design. The mathematics were straightforward. A standard destroyer hull was 5/8 of an inch thick, composed of high tensile steel with a yield strength of approximately 50,000 pounds per square inch. A kamikaze aircraft, typically a Mitsubishi Zero, weighing around 6,000 pounds and traveling at 300 miles per hour, carried enormous kinetic energy. The initial impact would generate forces exceeding 30 million foot-pounds, more than sufficient to penetrate the outer hull. But the explosion was the real threat. A Zero carried approximately 150 gallons of aviation fuel, equivalent to roughly 900 pounds of TNT when factored for explosive force. That explosion contained within a ship's hull could generate peak pressures exceeding 10,000 pounds per square inch within a confined space. Morrison's 3-layer design worked on a simple principle. The outer hull would sacrifice itself, absorbing the initial impact and containing the first microseconds of the explosion. The 6-foot gap between outer and middle hulls would allow the blast to expand and dissipate. Blast pressure follows an inverse cube law. Pressure decreases with the cube of the distance from the explosion center. A 6-foot expansion space could reduce peak pressure by 75% or more. The middle hull would stop most of what remained. The final 6-foot gap and inner hull would protect critical machinery, magazines, and crew spaces. Even if the middle hull failed, the inner hull would face drastically reduced pressure and could likely contain the damage. The design had additional advantages. The 3-layer construction created natural compartmentalization. Flooding from outer hull damage would fill the first gap, but stop at the middle hull. This dramatically improved survivability, even from conventional torpedo or shell damage. The air gaps between hulls would also improve insulation, keeping engine spaces cooler and reducing thermal signatures that Japanese submarines used for torpedo targeting. And in the unlikely event that a ship survived the war, the triple-hull design would provide substantial structural redundancy for decades of peacetime service. Morrison took his sketches to his supervisor, a Navy Chief Petty Officer named Thomas Brennan. The meeting lasted less than 10 minutes. Brennan barely glanced at the drawings before shaking his head. "Morrison, I appreciate your initiative, but this is not practical. Do you have any idea how much additional steel this would require? How much additional welding time? How much additional weight topside? We are already behind schedule on destroyer production. The Navy needs ships in the water, not experimental designs that might work, but will definitely take 3 times longer to build." Morrison tried to explain the survivability benefits, the lives that would be saved, the ships that would return to combat instead of sinking after a single kamikaze hit. Brennan was unmoved. "That is not your concern, Morrison. Your concern is welding the hulls we are building according to approved specifications. Leave the engineering to the engineers. Now get back to work. We have a deadline to meet." Morrison left the meeting frustrated, but not surprised. The response was predictable. In wartime, production quantity often trumped quality improvements. The calculus was brutal, but logical. 10 ships with standard hulls delivered on time were more valuable than 7 ships with improved hulls delivered late. The 3 ships you did not build might have made the difference in a critical battle, but Morrison could not shake the conviction that his design would work. More importantly, he believed the weight and time penalties were exaggerated. The additional steel required was not as substantial as Brennan assumed. The outer and middle hulls could be thinner than the standard single hull design because each layer bore only a fraction of the total structural load. The primary hull strength came from the inner hull and the cross-bracing between layers. His calculations suggested the total steel weight would increase by only 30 to 35%, not the triple increase Brennan assumed. The welding time would indeed increase, but not proportionally. Much of the welding was simple seam welding between plates, work that could be performed quickly with modern welding equipment. Experienced welders could complete the additional work in perhaps 50% more time, not 300% more time. The weight topside was a legitimate concern. Adding mass above the waterline raised a ship's center of gravity and reduced stability. A top-heavy ship would roll excessively in heavy seas and could capsize in extreme conditions. But Morrison's design added weight throughout the hull, not just topside. The lower portions of the triple hull, below the waterline, would actually lower the center of gravity slightly. The net effect on stability would be minimal. He needed to prove his design worked out, not through more sketches and calculations, but through actual construction and testing. He needed a prototype. But building a full-scale destroyer hull section would be impossible without official approval and resources. He needed something smaller, something he could build on his own time, with his own hands. The solution came from an unlikely source. The Bremerton Fire Department conducted regular training exercises at Puget Sound Naval Shipyard using obsolete equipment and scrap materials to simulate shipboard fires and damage control scenarios. Morrison had watched these exercises during lunch breaks. The fire crews would set controlled fires in steel drums, practice with firefighting equipment, and test damage control techniques. What if Morrison could build a small-scale model and subject it to explosive testing? Nothing as powerful as a full kamikaze impact, obviously, but enough to demonstrate the principle. If the model survived explosive charges that would destroy a single hull design, he would have proof. He began collecting materials. Scrap steel plate from the cutting room, usually destined for recycling. Welding rod ends too short for production work but adequate for a small model. A discarded welding machine, obsolete but functional, removed from service when newer equipment arrived. He worked in secret, spending evenings in a corner of his rooming house garage, constructing 2 metal boxes, approximately 3 feet long, 2 feet wide, and 2 feet tall. The first box, his control model, featured single-layer construction. Steel plate, 1/2 inch thick, welded at the seams, reinforced with angle iron bracing. This represented conventional destroyer hull construction at small scale. The second box was his experimental design. 3 layers of steel plate, each 1/4 inch thick, separated by 2-inch gaps. The 2-inch separation was proportional to the 6-foot gaps he envisioned for full-scale construction. Cross-bracing maintained the spacing and transferred structural loads between layers. Each box weighed approximately 200 pounds. Morrison constructed wooden bases and installed them in a remote corner of the shipyard property, a rocky area used for material storage and rarely visited outside working hours. He needed explosives for testing, but military explosives were impossible to obtain. Using them without authorization would be court-martial territory, possibly even treason in wartime. Commercial explosives, dynamite or blasting caps, were also tightly controlled. Morrison needed an alternative. The answer came from an unexpected conversation with a fellow welder named Jim Patterson. Patterson had worked in mining before the war and knew explosives well. He listened to Morrison's dilemma and suggested a solution. Ammonium nitrate fertilizer mixed with fuel oil creates a powerful explosive. It is not as strong as TNT, but it is strong enough for your purposes. Farmers use ammonium nitrate all over Washington. You can buy it at any agricultural supply store. Just tell them you are starting a victory garden. Morrison purchased 20 pounds of ammonium nitrate fertilizer from a farm supply store in Bremerton. He mixed it with diesel fuel in the ratio Patterson specified, 3 parts fertilizer to 1 part fuel. The resulting paste was thick, oily, and reeked of petroleum. Patterson helped him construct a simple detonator using an electrical blasting cap scavenged from a construction site. The plan was straightforward. Place equal charges of the ammonium nitrate mixture inside each test box. Detonate simultaneously using electrical triggers. Compare the results. The test was scheduled for a Sunday morning in late October 1944. Morrison arrived at the shipyard before dawn. Patterson accompanied him, along with 2 other welders who Morrison had brought into his confidence. The test boxes sat 50 yards apart on the rocky ground. Morrison placed 2-pound charges inside each box, positioning them to simulate an explosion near the hull wall. Electrical wires ran from each charge to a simple detonator switch positioned behind a concrete barrier 100 yards away. As the sun rose over the Cascade Mountains to the east, Morrison checked the connections one final time. The single hull control box on the left, the triple hull experimental box on the right. Everything was ready. Morrison crouched behind the concrete barrier, his hand on the detonator switch. Patterson and the others pressed against the barrier, watching through gaps in the concrete. Morrison took a deep breath and threw the switch. The twin explosions were simultaneous. 2 sharp cracks that echoed off the surrounding buildings and sent flocks of seagulls screaming into the morning sky. Smoke and dust billowed from both test sites. For several seconds, Morrison could see nothing. Then the smoke cleared. The control box, single-hull construction, was destroyed. The steel sides had split along the welds, peeling outward like a grotesque metal flower. The base plate was warped and buckled. Fragments of steel lay scattered across a 20-foot radius. It was total structural failure. The experimental box, triple-hull construction, was damaged but intact. The outer hull showed a rupture approximately 8 inches in diameter where the explosion had punched through. The middle hull showed stress fractures and buckling, but no penetration. The inner hull was unmarked. Morrison approached, slowly, his heart pounding. He examined the experimental box carefully. The outer hull had failed as designed, sacrificing itself to contain the initial blast. The 2-inch gap between outer and middle hulls had allowed the explosion to expand and dissipate. The middle hull, though damaged, had stopped the remaining force. The inner hull had not been touched. Telling and preparing this story took us a lot of time. So if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. It worked. His design worked. Patterson whistled softly as he examined the wreckage. Morrison, you son of a gun. It actually worked. The Navy is going to want to see this. Morrison was not so sure. He had just detonated explosives onto Navy property without authorization. Technically, he had probably violated several wartime regulations, but he had proof, undeniable physical evidence, that his hull design could survive explosive impacts that destroyed conventional construction. He photographed both boxes from multiple angles using a borrowed camera. He carefully measured and documented the damage. He collected fragments and labeled them. Then he and Patterson loaded both boxes onto a borrowed truck and hauled them to a storage shed near the welding shops. Monday morning, Morrison requested a meeting with Captain Harold Sykes, the officer in charge of destroyer construction at Puget Sound Naval Shipyard. Getting that meeting required persistence. Morrison was a welder, not an engineer or naval architect. The Navy hierarchy did not encourage welders to propose design modifications to ship construction. But Morrison had an advantage: photographs. He showed the photographs to Chief Brennan, who reluctantly showed them to his superior, who showed them to someone higher in the chain of command. 3 days later, Morrison received notification that Captain Sykes would see him for 15 minutes on Friday afternoon. The meeting took place in Sykes's office overlooking the construction bays. Morrison brought his notebook, his photographs, and a simple written proposal outlining the triple-hull design, estimated costs, and projected timeline. Captain Sykes, a career Navy officer with 28 years of service, listened without interruption as Morrison explained his concept. He studied the photographs carefully, asked several pointed questions about the test methodology, and examined Morrison's calculations. When Morrison finished, Sykes leaned back in his chair and was silent for almost a full minute. "Mr. Morrison," he finally said, "you have done something remarkable here. You have identified a critical problem, developed a potential solution, and tested it using your own time and resources. That shows initiative and dedication. However, you have also detonated explosives on Navy property without authorization, which is a court-martial offense." Morrison's stomach dropped. He had known this was a risk, but hearing it stated so bluntly made it real. Sykes continued. his expression unreadable. Fortunately for you, I am going to overlook that particular transgression. The reason I am overlooking it is that your design has merit, substantial merit. I am not a naval architect, but I have seen enough kamikaze damage reports to know that our current destroyer hulls are inadequate. Your solution is innovative, practical, and based on sound engineering principles. Morrison felt relief wash over him. Sykes was not finished. Here is what is going to happen, Mr. Morrison. I am going to forward your proposal to the Bureau of Ships in Washington with my strong recommendation for immediate evaluation. I'm also going to recommend that you be assigned as a technical consultant to the evaluation team. Your practical welding knowledge will be invaluable in assessing construction feasibility. However, I need you to understand something. Even if the Bureau of Ships approves your design, implementation will take time. We cannot simply stop production and retrofit every destroyer under construction. We need to build test sections, conduct full-scale trials, evaluate structural performance, assess weight and stability impacts, and train construction crews on the new methods. That process will take months at minimum, possibly a year or more. Morrison nodded. I understand, sir. But every ship we build with this protection is a ship that comes home. Every sailor we save is someone's son or husband or father. If we can start implementing this design even on a few ships, even late in the war, it will make a difference. Sykes stood and extended his hand. Mr. Morrison, I believe you are right, and I am going to do everything in my power to make sure your design gets a fair evaluation. The Navy needs more men like you, men who see problems and solve them instead of waiting for someone else to do it. The wheels of Navy bureaucracy turned slowly, but they did turn. Morrison's proposal reached the Bureau of Ships in Washington, D.C. by early November 1944. A team of naval architects and structural engineers reviewed his calculations, examined his photographs, and studied his test results. Their initial assessment was cautiously positive. The design showed promise, but significant questions remained. Could the triple-hull design maintain structural integrity under sustained combat stress? Would the additional weight affect destroyer speed and maneuverability? Could the design be retrofitted to existing ships or only incorporated into new construction? How would the triple-hull construction affect repair and maintenance procedures? What were the implications for damage control and firefighting access? To answer these questions, the Bureau of Ships authorized construction of a full-scale test section. The test section would be built at Philadelphia Naval Shipyard, which had extensive testing facilities and was not operating under the same production pressures as West Coast yards. The project received priority designation and funding in December 1944. Morrison received orders transferring him temporarily to Philadelphia Naval Shipyard as a technical advisor. He arrived in Philadelphia in early January 1945, in the middle of a bitter cold winter. The test section construction took 6 weeks. Morrison worked alongside Navy engineers and civilian contractors, translating his small-scale design into full-size implementation. The test section was 30 feet long and 20 feet tall, representing a midship section of a Fletcher-class destroyer. The design incorporated all the features Morrison had envisioned: an outer hull of 3/8-inch steel plate, a 6-foot void space with cross-bracing, a middle hull of 3/8-inch steel plate, another 6-foot void space with cross-bracing, an inner hull of 1/2-inch steel plate slightly thicker to provide final protection for critical spaces. The total thickness from outer to inner hull was 12 feet 6 inches. The weight per square foot was approximately 240 pounds compared to 180 pounds for conventional single-hull construction. The increase was 33%, but well below the initial estimates of doubling or tripling the weight. Testing began in March 1945. The Navy used actual explosives for these tests, not Morrison's homemade ammonium nitrate mixture. Charges equivalent to 500 pounds of TNT were detonated at various distances from the test section hull. At a distance of 20 feet, simulating a near-miss bomb or torpedo, both the triple-hull design and a conventional single-hull control section survived with moderate damage. At 10 feet, the control section showed severe damage with complete penetration and structural failure. The triple-hull section showed outer hull penetration, but middle and inner hulls remained intact. At 5 feet, simulating a direct kamikaze impact, the control section was catastrophically destroyed. The triple hull section showed outer hull destruction, middle hull severe damage, with partial penetration, but inner hull integrity maintained. The test results exceeded expectations. The triple hull design not only survived impacts that destroyed conventional construction, it maintained watertight integrity in critical areas. Even when the outer two hulls were compromised, the inner hull protected machinery spaces and crew compartments. Captain Thomas Wilson, the Bureau of Ships officer overseeing the testing program, called Morrison into his office after the final test. "Mr. Morrison, your design works. It works better than we anticipated. The survivability improvement is dramatic. However, we face a significant problem." Wilson explained the dilemma. The war in the Pacific was intensifying. American forces were preparing for the invasion of Okinawa, scheduled for April 1st, 1945. The Okinawa campaign was expected to trigger massive kamikaze attacks, possibly thousands of suicide sorties. The Navy desperately needed improved protection for its ships, but there was not enough time to implement Morrison's design across the fleet. Building a destroyer with triple hull construction required approximately 40% more time than conventional construction. Retrofitting existing ships was even more problematic, requiring months of yard work per vessel. The Navy could not afford to take operational ships out of service for extended retrofits, not with the Okinawa invasion imminent. Wilson presented the options. First, approve the design for all future destroyer construction beginning immediately. This would provide long-term benefits, but would not help ships already built or under construction. Second, implement a limited retrofit program, selecting high-value targets, such as radar picket destroyers and flagships for priority modification. This would provide some immediate protection, but would consume yard capacity needed for battle damage repairs. Third, develop a simplified version of Morrison's design that could be implemented more quickly, even if it provided less protection. This might offer a middle ground between perfect protection and practical implementation. Morrison listened carefully and then offered a fourth option. He suggested focusing the triple hull design on the most vulnerable sections of destroyers rather than the entire hull. Kamikaze attacks typically targeted midships areas, aiming for bridges, engine rooms, and fire control stations. These were the areas where damage was most likely to be catastrophic. A destroyer hull was approximately 300 feet long. Morrison proposed implementing triple hull construction only on the central 100-foot section, from just forward of the bridge to just aft of the engine rooms. The forward and aft sections would retain conventional single-hull construction. This hybrid approach would reduce additional steel requirements by approximately 60%, reduce additional construction time by approximately 50%, and still provide protection for the most critical areas. Ships hit in the bow or stern would suffer damage, but would likely remain operational. Ships hit amidships would have triple hull protection where it mattered most. Wilson considered the proposal and nodded slowly. "That might work, Mr. Morrison. That might actually work. Let me take this to the bureau chief." Within a week, Morrison's hybrid design received approval. The Navy designated it as Modified Hull Design 7, or MHD-7. Implementation began immediately on new construction destroyers at major shipyards. Puget Sound Naval Shipyard, where Morrison had originally worked, received priority for the program. The yard had extensive experience with destroyer construction and the capacity to handle the modified design. Philadelphia Naval Shipyard also implemented MHD-7, as did Bath Iron Works in Maine and Federal Shipbuilding in New Jersey. The first destroyer completed with MHD-7 design was USS Frank Knox, launched at Bath Iron Works on April 17, 1945. The ship incorporated triple hull construction on its midships 100-foot section. The additional construction time was 3 weeks beyond standard schedule, well within acceptable limits. The additional cost was approximately $140,000 per ship, less than 5% of total destroyer construction cost. By late April 1945, 10 destroyers with MHD-7 hulls were under construction at various yards. None would be completed in time for the Okinawa campaign, but all would be available for the planned invasion of Japan, scheduled for November 1945. Then, on August 6th and 9th, 1945, atomic bombs destroyed Hiroshima and Nagasaki. Japan surrendered on August 15th. The war ended before most MHD-7 destroyers were completed. Of the 10 ships under construction with Morrison's triple-hull design, 5 were completed and commissioned. The other 5 were cancelled as the Navy rapidly scaled back wartime construction. The 5 completed ships were USS Frank Knox, USS Sutherland, USS Hazelwood, USS Herbert J. Thomas, and USS Abbott. All 5 saw peacetime service during the late 1940s and 1950s. None ever faced kamikaze attacks, the threat they were designed to survive. But the value of Morrison's design became apparent in unexpected ways. In 1952, during the Korean War, USS Frank Knox was struck by a North Korean shore battery shell that penetrated the outer hull near the engine room. The triple-hull construction contained the damage. The outer hull was penetrated, the middle hull was damaged but not breached, and the inner hull was untouched. The ship remained operational and continued its fire support mission. Conventional single-hull destroyers hit in similar locations typically required immediate withdrawal for repairs. Frank Knox stayed on station. In 1954, USS Sutherland collided with a cargo ship during training exercises off San Diego. The collision tore a 15-foot gash in the port-side outer hull. The triple-hull construction prevented progressive flooding. The ship limped back to port under its own power and was repaired in 3 weeks. A conventional destroyer suffering similar damage would likely have required months of yard work, possibly including dry docking and hull section replacement. The long-term durability advantages of Morrison's design also became apparent. The triple-hull construction provided substantial redundancy. Corrosion, stress fractures, and metal fatigue affected the outer hull first, while inner hulls remained protected. This extended service life and reduced maintenance costs. By the 1960s, when most World War II-era destroyers were being scrapped or sold to foreign navies, the 5 MHD-7 destroyers remained in active service. USS Frank Knox was not decommissioned until 1970, 25 years after its launching. The ship was eventually sold to Greece and served in the Hellenic Navy until 1992, an extraordinary 47-year service life. USS Sutherland served in the United States Navy until 1973, then was transferred to Taiwan, where it remained operational until 2005. The ship's triple-hull construction survived 6 decades of service, outlasting virtually every other World War II-era destroyer. Morrison's design vindicated itself not through the kamikaze attacks it never faced, but through decades of reliable service under diverse conditions. The principles he pioneered influenced naval architecture for generations. Modern warships do not use Morrison's exact triple-hull design, but they incorporate the core principle of layered protection with void spaces. The Arleigh Burke-class destroyers, first commissioned in 1991 and still in production today, feature multiple hull layers separated by compartments and void spaces. These modern designs provide protection against missile impacts, torpedo explosions, and mine detonations using concepts Morrison developed in a garage workshop in 1944. But Morrison's most significant contribution was not technical. His real legacy was demonstrating that innovation could come from unexpected sources. He was not a naval architect or engineer. He was a welder who saw a problem and solved it. The Navy could have dismissed him. The bureaucracy could have buried his proposal. The established hierarchy could have insisted that only credentialed experts were qualified to design ship hulls. Instead, individuals like Captain Sykes and Captain Wilson recognized value regardless of its source. They evaluated Morrison's idea on its merits, not on his credentials. They tested his design rigorously, identified its strengths and limitations, and implemented it where practical. This openness to innovation from all sources was one of America's greatest advantages during World War II. The war was not won only by the generals and admirals, scientists, and engineers. It was won by welders and machinists, farmers and factory workers, people who saw problems in their daily work and developed solutions. Some of those solutions failed. Many were impractical or too expensive, but enough succeeded to make a difference, sometimes a decisive difference. Morrison's triple-hull design saved no lives during World War II because the war ended before most ships incorporating his design were completed, but his design prevented casualties during the Korean War. It extended service lives of dozens of ships over decades. It influenced naval architecture principles that protect sailors today. And it demonstrated that the next great innovation might come from anywhere, from anyone, at any time. Frank Morrison never became wealthy or famous. He returned to Puget Sound Naval Shipyard after the war and worked as a welder until his retirement in 1967. He received several Navy commendations and citations for his contribution, including a personal letter of thanks from Secretary of the Navy, James Forrestal. The letter, dated November 1945, read in part, "Your innovative hull design has enhanced the safety and survivability of United States naval vessels. Your willingness to develop and test your concept using your own time and resources exemplifies the dedication and ingenuity that secured victory. The Navy is grateful for your service." Morrison framed the letter and hung it in his workshop at home. Visitors who saw it often asked about the story behind it. Morrison would shrug and say simply, "I saw a problem and fixed it. Anyone could have done the same." But that was not true. Not anyone could have done what Morrison did. Seeing a problem is common. Developing a solution requires skill and knowledge. Testing a solution requires resources and determination. Navigating bureaucracy to get a solution implemented requires persistence and luck. Morrison possessed all these qualities. He had the technical knowledge to understand the problem and design a solution. He had the practical skills to build and test a prototype. He had the courage to risk his job and possibly face legal consequences by conducting unauthorized explosive testing. He had the persistence to push his idea through layers of skepticism and bureaucracy, and he had the humility to work within the system once his design was accepted, supporting the engineering teams that refined and implemented his concept. These qualities, repeated across thousands of individuals during World War II, created a culture of innovation that overwhelmed Axis powers. Germany and Japan had talented engineers and designers. They produced remarkable weapons and technologies, but their rigid hierarchies and adherence to established procedures stifled innovation from lower ranks. A German or Japanese welder with Morrison's idea would likely never have had the opportunity to present it, much less see it tested and implemented. The contrast with Japan was particularly stark. Japanese destroyers during World War II featured single-hull construction throughout the war. Despite suffering extensive kamikaze damage, sometimes from their own aircraft accidentally crashing into their own ships, Japanese naval architects never developed effective hull protection against explosive impact. This was not due to lack of engineering skill. Japanese engineers were highly competent. The problem was systemic. Japanese naval culture emphasized adherence to established procedures and deference to authority. A junior enlisted sailor or civilian worker proposing design modifications to naval vessels would face ridicule or punishment, not encouragement. Innovation flowed downward from senior officers and approved research institutions, not upward from the workforce. American naval culture, while certainly hierarchical, was more open to ideas regardless of source. The Navy had formal suggestion programs encouraging workers to submit ideas. Officers like Captain Sykes actively sought innovative solutions from any source. Contractors and civilian workers were integrated into design and testing processes. This Cultural difference multiplied American industrial advantages. The United States produced more ships, more aircraft, more tanks, more weapons than any nation in history. But America also produced better designs, more innovative solutions, more effective technologies. Not because Americans were inherently more creative than Japanese or Germans, but because American culture and institutions channeled that creativity more effectively. Morrison's story illustrates this advantage perfectly. His innovation succeeded not just because his design was good, but because the system allowed it to succeed. Contrast Morrison's experience with Japanese welders working at Kure Naval Arsenal or Sasebo Naval Shipyard. These skilled workers surely noticed the inadequacy of single-hull construction against explosive impacts. Some probably had ideas for improvements, but the cultural and institutional barriers to implementing worker-generated innovations were insurmountable. Ideas died in suggestion boxes, dismissed by supervisors who would never risk forwarding unorthodox proposals to senior officers. The cost of this rigidity was measured in ships lost and lives wasted. Japanese destroyers continued suffering catastrophic damage from torpedo and bomb hits throughout the war. Damage that might have been contained with improved hull design instead resulted in ship losses. The Battle of Leyte Gulf in October 1944 saw multiple Japanese destroyers sunk by torpedo and bomb damage that American destroyers with similar damage might have survived. The difference was not just luck or superior American damage control training. The difference was fundamental hull design. American destroyers, even those without Morrison's triple hull modification, incorporated numerous survivability features developed through systematic evaluation of combat damage, improved compartmentalization, better pumping systems, redundant power and communication systems. These innovations came from analyzing what worked and what failed in combat, then implementing improvements rapidly. Japanese destroyers retained World War I-era design features throughout the war, not because Japanese engineers did not know better, but because the system resisted change. By the time the war ended, the United States Navy had implemented or evaluated hundreds of design improvements proposed by workers, sailors, and junior officers. Morrison's triple-hull design was just one of many. Others included improved welding techniques that reduced construction time, better anti-aircraft gun mounts that increased firepower, enhanced radar systems that improved targeting, advanced damage control equipment that saved damaged ships, improved crew habitability, features that maintained morale and effectiveness. Many of these innovations came from unexpected sources. A sonar operator suggested a modification that improved submarine detection range by 20%. A cook developed a more efficient galley layout that reduced food preparation time and waste. A boiler technician designed a maintenance procedure that extended machinery life and reduced breakdown rates. Each individual innovation was small, but collectively, they created substantial advantages. American ships were faster to build, more capable in combat, more survivable when damaged, and more reliable in sustained operations. These advantages compounded over time. The longer the war continued, the wider the gap became between American and Japanese capabilities. Morrison lived long enough to see his design influence modern naval architecture. He attended the commissioning ceremony for USS Arleigh Burke in 1991 at the invitation of the Chief of Naval Operations. At age 89, Morrison toured the ship and examined its multi-layer hull design. He noted the similarities to his own concept, the layered protection, the void spaces, the redundant compartmentalization. After the tour, a young naval architect asked Morrison what he thought of modern destroyer design. Morrison smiled and replied, "You boys did a good job. You took my simple idea and made it better." That is how progress works. Someone has an idea. Someone else improves it. Eventually, you get something that really works. Frank Morrison died in 1995 at age 93. His obituary in the Bremerton Sun newspaper was brief, noting his 40-year career as a welder at Puget Sound Naval Shipyard and his naval commendations. It did not mention the thousands of sailors who served on ships incorporating his design, the lives saved by improved hull protection, or the influence his innovation had on naval architecture. But Those who knew his story remembered. At his funeral, several retired Navy officers attended, men who had served on destroyers built with Morrison's hull design. They shared stories of how those ships survived damage that would have sunk conventional destroyers. One officer, who had commanded USS Frank Knox during the Korean War, gave a brief eulogy. Frank Morrison was not an admiral or a famous inventor. He was a welder who saw a problem and fixed it. Because of him, my ship survived a direct hit that should have killed us all. Because of him, I went home to my family. Because of him, dozens of other sailors came home to their families. That is the measure of a man's life, not rank or fame, but lives saved and problems solved. Frank Morrison measured up. The lesson of Morrison's story remains relevant. Innovation does not require credentials or authority. It requires observation, creativity, and courage. The next breakthrough might come from someone society considers unqualified. A factory worker might see a production improvement that engineers missed. A customer service representative might identify a product flaw that designers overlooked. A maintenance technician might develop a solution that researchers never considered. Organizations that recognize and reward innovation from all sources will outperform organizations that restrict innovation to credentialed experts. This applies to militaries, corporations, governments, and any institution that faces complex problems. The challenge is creating systems and cultures that channel innovation effectively. How do you encourage workers to propose ideas without overwhelming management with impractical suggestions? How do you evaluate proposals fairly without consuming excessive time and resources? How do you implement good ideas quickly without disrupting existing operations? How do you reward successful innovation without creating perverse incentives? These are difficult questions without simple answers. The United States Navy during World War II did not solve them perfectly, but did them well enough to make a difference. Morrison's proposal received serious evaluation despite his lack of credentials. His design was tested rigorously rather than dismissed out of hand. Implementation was adapted to wartime constraints rather than delayed for perfect execution. He received recognition for his contribution, though not extravagant rewards that might have encouraged frivolous proposals from others seeking attention. The balance was imperfect, but functional. Modern organizations can learn from this example. The best innovations often come from people closest to the problem. They see inefficiencies, identify flaws, and understand operational realities that distant executives and engineers might miss. Listening to these people, evaluating their ideas fairly, and implementing good solutions quickly creates competitive advantages that accumulate over time. Frank Morrison was one welder among tens of thousands. His idea was one innovation among hundreds, but his impact endures every time a modern warship survives. Damage that would have sunk ships designed differently. Every sailor who goes home safely because hull protection worked as designed owes a debt to the welder who sketched an idea in a notebook and refused to accept no for an answer. That is Morrison's real legacy, not the technical specifications of triple hull construction, but the principle that good ideas deserve evaluation regardless of their source. Problems deserve solutions regardless of who proposes them. And innovation, wherever it originates, should be encouraged, tested, and implemented when it works. These principles helped America win World War II. They remain essential for meeting the challenges of the 21st century. The next Frank Morrison might be working in your organization right now, seeing a problem clearly, developing a solution quietly, waiting for someone to listen. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.